to the CCENT journey with me, Ryan. In this next section, we're going to have a discussion around the differences between a local area network, a LAN, and a wide area network, a WAN. We'll then jump into the designs, having a discussion around a 3-tier hierarchical design and a collapsed core. And then we're going to finish off talking about Unicast, Multicast, and broadcast traffic. For those who don't know, you can contact me here on YouTube, on LinkedIn, or Twitter. So let's start with a quick overview of what is a LAN versus a WAN. A LAN stands for Local Area Network. It's a network that is normally confined to a relatively small area. It is generally limited to a geographic area such as a company, a school, or building. And a WAN, a wide area network, connects networks in a larger geographic areas such as London, United Kingdom, or the world. WANs are used to connect offices together like schools and buildings. So let's go for an example here. We have a look at this diagram that we've got in front of us at the moment. It's kind of a half-finished diagram. That's because we're going to have a discussion around it and finish it together. Now, first of all, you can see I've popped this dotted line down through the firewall, and I've marked this a demarcation point. Now, what a demarcation point is essentially is a point where the responsibility of one supplier hands over to the other. So, for example, here in the WAN, let's say this is our ISP, our internet service provider, or maybe it's just a service provider. Essentially, they're providing us with these dual HA, high availability pairs of firewalls, and their demarcation is through the firewall, meaning that if you had a problem with this device, or if you had a problem with this device, it wouldn't be supported by the actual service provider who supplies the service to you. Now, you can see here I've marked the cloud as a WAN, and we previously talked about what a cloud represents in a diagram. We said that a cloud represents something that we don't necessarily care about or we don't necessarily know about. So for example, this could be the WAN, but it could be linking maybe to another site that we have with this WAN provider, or maybe along with or instead of, it may also give us a link maybe to the internet. A WAN is essentially grabbing these sites. Let's say, for example, this is in the UK and this particular site is in the US of A, and it allows them to actually communicate together. Now, your WAN might be the access technology here, might be something like just a leased line. It could be something like DSL connectivity, a cable connectivity, or something different, depending on the sort of size of the office. Depends on what access technology you would buy to actually connect that into the WAN. Now, moving on to a LAN would be something that's actually behind this particular WAN. So, for example, let's say this is another office in the US of A, and on the back of this particular router they have maybe a bunch of switches, and off the back of these switches they have a ton of PCs plugged into them. This would be considered a LAN. Same as to be true over here. This would be considered a LAN. Now, sometimes the concept of a LAN and WAN can be someone's perspective on it. So, for example, let's say that in this site down here in the UK, this happens to be where our headquarters are, and on the back of these switches here, we have maybe a long fiber to maybe a data center, for example, and down here a long fiber to another data center, and in these data centers are a bunch of customers, and we hand off, let's say this particular company here hands off connectivity to all of these providers. Well, each one of these customers would consider this to be their WAN, whereas this provider would consider this to be their WAN. So the terminology of WAN and LAN is essentially not only someone's perspective on it and where they are in the network, but also these kind of like general guidelines that I've put up here, because it's normally represented to the geographic area that they're plugged into. Okay, so in this next section we're going to have a discussion around unicast, multicast and broadcast. Now unicast, multicast and broadcast happens at both layer 2 and at layer 3. Remember, layer 2 is the data link layer, and this is where devices like switches live, and layer 3 is the network layer, and this is where devices like routers live. Now switches, they actually, or layer 2 I should say, use MAC address for communication, and layer 3 uses IP addresses for communication. Now in the next couple of videos we'll discuss in a bit more detail about IP addressing and MAC addresses, but for now we're going to have a high level view of what the different types of messaging like unicast, multicast and broadcast allow us to do. Now unicast can be thought of as something very simple. Essentially unicast is a one-to-one communication. So if we just draw a switch, remember this is the icon for switch, and off the back of this switch we have, let's say, a PC and another PC, and let's say another one, and PC1 wants to speak to PC3, and PC1 is able to, let's say, communicate with that PC directly without involving PC2. This is considered unicast because it's a one-to-one communication. When we think about the others, which is multicast and broadcast, this is where it gets a little bit more complicated. So multicast essentially means one to many. Now multicast example would be, let's say we have another PC down here and we're running some sort of multicast technology or multicast protocol, which is way beyond the scope of the CCENT and the CCNA, but I want to use it for sort of a theory. Let's say, for example, PC1 is streaming some sort of video. What can happen is PC3 and 4 will be set up to listen to that video, so the switch would know to send that communication to 3 and 4 but not to 2. This is a multicast communication. So it's not to everyone, but it is to more than one. So another example of this is, let's say we have our routers, and our routers connect into a switch, and at the back of the switch we also have two PCs. Let's put another router up here. Now let's say these routers are running RIP, which is the Routing Information Protocol, and we're going to be running version 2, because version 2 takes use of multicast, whereas version 1 uses broadcast. So RIP, responsibility of RIP, we've not discussed this in detail yet, but RIP essentially is to advertise subnets to one another. So off the back of this router, let's say we have 192.168.0.0/24. The back of this router we have 172.16.0.0/24, and on the back of this router we have 10.0.0.0/24. And all these routers are on the same subnet. Let's say he's a .1, he's .2, .3, and even these PCs are on the same subnet. Now RIP, the responsibility of RIP is to advertise the routes, or advertise prefixes to one another. So for example, let's say this guy here, he's aware of the 192.168.0.0/24, but this particular router doesn't know how to get to 192.168.0.0/24. So RIP can be used to advertise this router as a gateway for 192.168.0.0. So if this particular router had a packet destined for that destination, it will know, I know how to get to 192.168. To get there, go to dot 3, because dot 3 knows how to get there. But that communication, if you like, happens via multicast. And the way that works is every router on the link, every so many seconds, will actually dump, if you like, or send a list of all of the routes that particular router is aware of to a particular multicast address. And that multicast address is 224.0.0.9. And that's a layer 3 IP address. And when it comes out onto the wire, this router and this router will be listening for packets destined to this IP. And when those packets come in, they will actually be, the information will be able to be interpreted and learned. These PCs down here will not be listening for the 224.0.0.9, therefore the traffic will not be sent to the actual PCs themselves. So what we have again is multicast, where even though they're all on the same segment and they're all on the same subnet, only 3 of the devices are communicating through multicast communication. Now if we were not running 2 and instead we were running 1 uses broadcast, which means instead of the 224.0.0.9 address, it's actually 255.255.255.255. This means everyone. So when this router now sends out its routing update to say, hey everyone, these are the subnets that I'm aware of, it will go to every single host. This PC would have to accept that packet in, process that packet, realize it's not for the PC, and drop it. The downside being a few reasons. One, we're using utilization of the NIC card of this PC, processing packets that are not relevant. 2, it's a big security concern. If there is a rogue PC plugged into this particular network and running something like Wireshark, he or she will be able to capture traffic or essentially routing updates from your router and then know what particular routes exist on your network. So the differences between unicast, multicast and broadcast. Unicast is a 1-to-1 communication. Multicast is a 1-to-many communication, and a broadcast is everyone. Later on, when we discuss things like ARP, the address resolution protocol, you'll see how the ARP process uses broadcast to communicate with everyone initially, but once it learns where the hosts live on the network, it then uses unicast to communicate with them. And when we come to ARP, this is where your foundation of unicast and broadcast, etc., will actually come to light. And when we get into things like routing protocols, this is where things like multicast will come together for you. Okay, so in the last section of this video, we're going to have a discussion around the designs. There are 2 designs, the Tier 3 design and the collapsed core design, that are outlined in the CCENT blueprint for ICND1 v3. The 3-tier design is the one I've got below us, which is the core, the distribution and the access. Each layer has its own, or each tier has its own job in this role, and what I want to do is just discuss them in a bit more detail. So access, this is where your end users actually access the network. So normally if we think about your PC at your office sitting on your table, you'd normally have a cable that runs down into the floor, and then underneath the floor you'd have it kind of trail back, if you like, to a cabinet and plug into a particular switch. Everyone else's cables would come back under the floor and also plug into this particular switch. This is the access switch. It normally sits inside the building, or so does the distribution and even the core, depending on the size of the building. But let's say this is just a single floor and it has just a single access cabinet. What you also see here is not only is it your PCs that connect into the access switch, but normally 9 out of 10 times, if you're taking or making use of VoIP, voice over IP, normally it's your phone that actually plugs into the switch. So we think about this cable again, it will come out the floor port, but instead of going to your PC, it'll actually go to a desk phone, and then this desk phone will then plug into your PC. The desk phone will get power from these access switches using power over Ethernet, and your PC traffic, if it needs to communicate with anything else, would actually go through the switch, through the VoIP device or through the phone, and then back down through the actual switch itself. And the switch is set up to accept both the VoIP and the PC communication, and has the ability to cipher which communication is, or which communication belongs to which device. And because it's able to do that, it's also able to put something called QoS, which is quality of service, on the VoIP communication to ensure it has higher priority as it traverses through the network. Now, access technology, access tier is also where your wireless APs tend to sit. I have seen quite a few designs where it plugs into the distribution, but it can plug into the access. When you're thinking about these sort of 3-tiered designs and these collapsed core designs that have been released, these are a theoretical and sort of recommended design. Doesn't necessarily mean that's the best way, depending on your design of your company. So you may see different designs for different reasons, but it's certainly a good by the book to sort of follow, to have to deploy an enterprise design. Now, when we think about the access layer, we have to think about what traits we would expect from the access layer. Now, normally you would expect to see high port density. After all, this is where all our devices across our company is going to be plugging into, so you'd want a lot of ports, and the more ports you have, you tend to then get low cost per port. For example, if you bought a 24 port switch for 1,000, and then you could have bought a 48 port switch for 1,300, obviously it's cheaper to go for the 48 port in the long run. Obviously, again, depending on the size of your company and so forth, but ideally you're looking for low cost per port and high port density at the access layer. Depending on the access layer, 9 out of 10 times it's probably going to be layer 2. Layer 2, like I said, is the data link layer, and what we expect at the data link layer is switches, and because it's switching, you'd also expect layer 2 technologies, so things like spanning tree protocol, VLANs, and so forth will be running in this area of the network. The access layers will also have a resilient uplink, so you can see that there are 2 ports connecting up to the distribution for resiliency. Now, as we move up to the distribution area, this is where essentially all of our access aggregates. The distribution layer is where a few things happen. First of all, it's where layer 2 becomes layer 3 in a sense. So above the distribution layer here, this is where we'll be running our routing protocols to control how we'd reach the destination. Distribution layer is also where things like access control takes place. So can a particular department speak to another department? This is also where policy-based routing takes place, if any. Also, we need to put in consideration the speed and power of these distribution switches. So for example, if we have 48 ports here, all that 100 megabits per second, we need to make sure that this particular distribution switch is going to be able to handle the maximum speed that each switch is able to output towards these uplinks. And if it's not able to handle it, what sort of effect that's going to have on the overall design. So if there's going to be some sort of bottleneck in the network, we need to be aware of it at the distribution and, to be fair, at the core layer. And so we need to be monitoring these links. To review the distribution tier, it allows the aggregation of multiple access layer devices. It's important to ensure that the distribution layer has enough bandwidth to process the total volume of traffic from all connected access switches. This is where security policies exist, like access control lists and filters, it will continue to honour any QoS that has been put on the access layer. As it reaches the distribution layer, it will go upstream towards the core. The core is primarily there for one reason only, and that is very high throughput. What we don't want to be doing here is essentially doing any access control, so any security or any filtering or any policy-based routing, anything that essentially would affect the CPU or overall capability of these core devices. All of that should have been done by the distribution layer before it gets to the core, because the core itself would be connecting multiple distribution layers together across the rest of the network. It doesn't want to be actually dealing with a lot of the overhead and complexities that the distribution layer should have attended with. The core is also referred to as the backbone. And in the collapse core design, which I'll show you in a moment, the collapse core design essentially does not have 3 tiers. In fact, normally the core is collapsed with the distribution, hence why it's called a collapse core, and there's normally access and core, no distribution, and that's referred to as a collapse core. Okay, so here we have a collapse core design. First of all, you'll notice that all I've done is deleted what was previously the core and relabeled the distribution to be distribution/core. Now, this particular design still keeps some of the traits that we've seen in the 3 tier. So the access layer still needs high port density, low cost per switch port. It has scalable, dual, resilient uplink ports. It also deals with normally layer 2 here, and above the distribution towards what would have been the core is still going to be layer 3. But the problem with this sort of design is it requires the distribution to be fully meshed. So I'm going to bring up another diagram to sort of explain what I mean by that. So here we have a expansion, if you like, on the view that we just looked at. So previously we looked here. We had a access layer, which you can still see is here. But what's happening now is we have the distribution layer, but notice that each building having only 2 tiers, access and distribution, the distribution needs to be fully meshed with all the other buildings. There's no centralized place that they can actually connect back to, for example, the core. And this is the downside when you go for a collapse design. Now, the reason you might be wondering why would someone go for a collapse design, well, primarily it's due to lower cost to the initial build. But what you do find is if you save that cost at the beginning, it becomes very difficult to scale this collapse core design moving forward, because the cable requirements increase dramatically, and each new building still requires a full mesh to all the other buildings because there's no centralized core it can get back to. It also increases things like routing complexities as new buildings are added, and additional routing peers are needed in the routing protocol. So normally it's recommended, again depending on size, design and other requirements, to have that 3-tier hierarchical design where we would have a similar thing to what we have now, what you can see on the screen, but instead we would have a core in the middle, and there will only be 2 links from every building, or maybe 4 links from every building, uplinking to a core, and therefore there'd be less need for routing peers, there'd be less confusion around the cabling, and in turn it'd be easier to troubleshoot, diagnose and ensure that the network is performing the way it should be performing. Okay, so that's all we got time for this lesson. Hopefully that's been informative. I put a comment here, so I thought that was going to be a quick one. I bet when you most likely seen the LAN and WAN, you've probably thought this was going to be a quick, easy lesson, but obviously not, because we got into more complex around the designs and the types of communications that exist. But the reason I put the LAN and WAN there, which most likely, well, arguably more of a prerequisite for the exam, is to make sure we're all on the same page. So the WAN stands for Wide Area Network, and the LAN stands for Local Area Network. Local Area Network is essentially your local network that's geographically something like a building, for example, and a WAN is what connects multiple LANs together. We also then went into Unicast, Multicast and Broadcast. We said that a Unicast is a 1-to-1 communication. We said a multicast is a one-to-many. And we also then said a broadcast is a one-to-all. We had a discussion around RIP, the Routing Information Protocol, and how version 1 uses the broadcast, but version 2 uses multicast, and how that may affect multiple PCs and routers that are connected to the same segment. We also then said ARP. We said that ARP would use something like broadcast to begin with. Then once it learns where all of the hosts live on the network, it will then start to use unicast communication. And later on, when we get into understanding Ethernet in more detail, we will touch base on how ARP works and how it actually broadcasts out, and look at some Wireshark captures of how that looks. And then we finished with designs. We had a brief, well, actually a quite in-depth look at, to be fair, of the 3 tiers, which was the access, the distribution and core. We had a discussion around what you would expect at each tier, and then a collapse core. We explained essentially a collapse core is where you collapse the distribution and core into one tier, so you're left with the access and what some people would call the dist / the core, and why this sounds like a great idea to begin with and a great cost saving scheme, if you like, but we know later on as the designs becomes more complex and we don't have that centralized core to essentially connect everything back to, that we end up in this full mesh and very hard to troubleshoot network. So I'd like to thank you for viewing, and I hope this has been helpful, and if it has been, please do like and subscribe.